Okay, again to highlight, once you take a look at your datasheet, you have to be alert on this value, which is your capability of the device. The junction temperature should not rise above the limit. So the energy here is converted into heat. So we can measure the heat throughout the external mechanism or external structure of the device, especially on the tap, metal tap, and on the heatsink itself. So once the heat generated inside the junction, we have three kind of heat propagation, which convey the heat out to the ambient. It may be propagate throughout conduction, which is direct contact, throughout radiation, electromagnetic wave, throughout convection, which in terms of liquid base. So in general, what convection means that the heat is removed by transferring the energy throughout the fluid. That could be a mix of hot and cold air, and also by natural or forced convection throughout the formula here. So we can see there's the formula is a fixed formula. We have a fixed, so we have here H as a constant, and A is the surface area. So through convection, it depends on the surface area, and same goes to the conduction mode. And you can see that from the formula here, the conduction rate is also depend on the surface area. Heat transfer by contact, maybe in liquid cooling techniques, it use this kind of conduction. And we have on another slide, which is the heat propagate throughout radiation. So we have here also, it depends on the surface area. So the flow of the heat in the infrared section of the electromagnetic spectrum. Okay, this is just a general knowledge on how the heat is transferred from the heat source, which is junction just now, throughout to the ambient. So we need to remove all the heat that being produced at the junction, such that the temperature of the junction could be kept below their specific range. So the thermal energy which is created at the junction is considered as dissipated power or losses power, which indicate here as PD, and dissipated power, PD. So it requires that the device to transfer all the heat that being generated here to the outside world, which we also refer as ambient. So ambient here is referred as a mass surrounding of a material or device. Let's say we have a converter that operates encapsulated in the case. So the case, the environment inside the case, if it's not affected by the heat that being generated on the device, and the temperature of the surrounding air inside the device is not changed much with the operating of the device, so the inside ambient, the inside air of the converter is considered as ambient. So we indicate ambient as TA, ambient temperature. So in the certain datasheet, we have here how much the maximum device can dissipate. This is PD. We have the table here from each of the datasheet. We have here how much the device can withstand. If for this device, it can withstand up to 55.6 watt. So this is not the processing power of the device, but this is the capability of the device in terms of to dissipate heat. When the device process the power and process the voltage and current, if it delivers certain voltage and certain, it processes certain voltage and certain current throughout the system. But this is the losses that should be dissipated by the device. This is the maximum capability of the device. It can withstand up to 56.6 watt. Provided that the case temperature is maintained off at 25 degrees C. If the temperature is rise more than 25 degrees C, beyond temperature of the room temperature, so you have to take note on this term. You should derate on value of 0.38 watt per degree C. So means that in every 1 degree C of increment, you have to minus 56.6 minus 0.38 for each of 1 degree C increment beyond or above 25 degree C. So we calculate later on certain scenario. So this is what stated inside the datasheet. So next slide shows the Fourier heat transfer law, the modified for thermal equilibrium. For conduction mode, we have the rate of heat transfer, which depend on the constant of convection heat transfer coefficient, and also the cross-sectional area, the surface area of the device to transfer heat to the ambient. So it means that the rate also depend on the surface area and cross-sectional area. So the heat removal, thermal ability of the device requires heat dissipation at rate which is bigger than how much it be generated inside the junction. So we can imagine that we have a tank of a pool. If the rate that the pipe pouring water into the pool is more than the outlet, so what will happen that the pool will overflow. So we have to have some sort of outlet that bigger, much bigger than the water that pour into the pool itself, to maintain from the pool from overflow. So that's the concern now. We have to have a thermal ability of the device to dissipate heat at much larger rate compared to the what being generated in the junction. So if we combine the previous equation that described in the ability of the device to affect the transfer of the thermal energy by conduction and also by conductivity, so high conductivity is required. So instead of here, the dPd, the amount or the rate of dissipated power over the junction temperature, this is the device considered as device thermal conductance. So we have in terms of thermal and electrical analogy, if we replace or redraw thermal equation or thermal circuit from electrical or electrical to thermal, thermal to electrical, we can replace in terms of voltage to T, temperature, the delta V to delta T, current represented by dissipated power, P is replaced by heat, conductivity by also thermal conductivity, resistivity is a resistivity as well. So we'll take a look later on how that table going to be used. So in terms of junction to case thermal resistance, so we have in the table of each datasheet that we have previously reviewed, we have here certain parameter which labeled as R theta JC. Some datasheet they rewrite as R TH. TH means thermal from J to A. So this one R thermal JA, R thermal J ambient. This is R thermal JC, R thermal JA, R thermal JA. Means that R, this is the thermal resistance between junction to case, JC. This is the thermal resistance between junction to ambient. At other scenario, the value is different. So from thermal system from junction to ambient, but the value is different because of different scenario. So this is from thermal from junction to ambient to mounting base, to mounting base to case, junction to mounting base. This is from the junction to ambient in free air. We can see the value is different. We take a look later on why it was different. So the dimension of thermal resistance maybe will indicate as degrees C per watt. Some datasheet they represent as Kelvin per watt. Both are the same. So the thermal resistance or effective thermal resistance can be defined as temperature rise of a designated junction above the reference point per unit power dissipation under condition of thermal equilibrium. So consider as the device which is stand alone, it does not mounting yet on any kind of heatsink or external heat transfer or heat exchanger structure. So it can be represented as a device which have a heat that generated at the junction and transfer to the case. Junction inside here, case is the metal tab here. So the metal tab we have here, junction inside the body of the plastic encapsulated case here, PN junction. It will generate heat and deliver or convey out to the case. So heat generated here, transfer to the case throughout the circuit which have a thermal resistance of R thermal from J to C. If we rewrite again or redraw in terms of thermoelectrical analogy, we can have a representative of PD as power source or current source, which complete the circuit throughout junction to the case. So R thermal JC. So it is required that the thermal resistance should be very low, so that the thermal conductivity should be at highest possible.